Good morning, afternoon, evening, depending on where you are, and welcome to the Open Systems Media series on designing for AI. In this episode, we are looking at AI in healthcare. This episode is sponsored by Microchip and Starlab Software. In earlier episodes, we're doing these one per month. So in other months, we looked at different aspects of designing with AI, and all of those episodes are available on demand, and that'll be the case going forward as well. You can find links to those webcasts in the handouts tab in the console that you're looking at right now. My name is Rich Nass. I will be your moderator for this event. I am also the Executive Vice President of Open Systems Media. I lead the content team for embedded computing design. If you are not familiar with embedded computing design, shame on you. It's a great resource for anything related to design of hardware and software for embedded systems. You can find it at www.embeddedcomputing.com. It's filled with design articles, blogs, white papers, videos, podcasts, and lots more. So as I mentioned, this is part of our series on AI. In the past, we talked about smart manufacturing, security, and stuff like that. In upcoming installments, we'll look at AI in the automobile, smart buildings, predictive maintenance, and so on. But let's get back to the subject at hand right now, AI in healthcare. As you are aware, AI is being deployed in pretty much every aspect of healthcare. And there's lots of different things that go into that. One of those is definitely security, which is a top priority. So in this session, we will be looking at how low power devices can implement AI in the wearable space, and what's being done to make sure that they remain safe and secure. You'll be hearing from three experts today. Martin Smith is the medical and health segment manager at Microchip. Nilim Riparelia is the one who leads Microchip's go-to-market efforts for AI and ML on edge devices, as well as 5G and communications markets. And then finally, you'll hear from Adam Frazier, and he is the Chief Operating Officer at Starlab Corporation. Before I bring out our experts, let me go over some of the housekeeping stuff. The entire presentation will take about 45 minutes or so, and that'll leave us some time to answer your questions, and we'll answer as many as we have time for. On the right-hand side of the console window, you'll see an area where you can enter those questions in real time. And as I said, we'll answer as many as we can when the three speakers are done. If we do not have a chance to answer your question as part of the webinar, somebody will get back to you after it's over. So we answer everything, just we may not have time to do it as part of the webcast. If you have a question pertaining to the operation of the webcast, like if your slides aren't advancing right or the audio doesn't sound right, put that into the question box and one of our tech folks will get back to you with a fix. There's also a tab there that says handouts. If you click on that, you'll be able to download a copy of the slides that are being presented today. You'll also see the registration for those other events that I mentioned as well. This particular webcast will be available in archive version shortly after we're done. So if you missed something, if you want to go back and review, you want to send it on to a friend or a colleague, it'll be there for you. Okay, that's it from me. Let me hand it off to Martin to get us started. All yours, Martin. Take it away.
Hey, thanks, Rich. Appreciate it. And good morning, good afternoon, and good evening to all of you. Today, I'd like to give you a little bit of an overview of artificial intelligence and machine learning in healthcare, and more of a bigger picture look. Nilam will go into more of the technical requirements and some of the aspects of that, but to look at some of those challenges, requirements, and opportunities that we're seeing in healthcare. Now, the question would be, why would anybody really care about the big picture? I mean, we're all going to go off and design, and we're going to get our hardware and software designs together and train our models and do all of that. But why would anybody really care about the bigger picture of that? Usually people would say that's more of a management issue, or maybe my regulatory department's issue as far as how we go to FDA or to the EU MDR, whatever markets we're going into. But I think as engineers, it's important to understand going forward in the future and proposing, we can understand what's being accepted in the marketplace now and what's being accepted by the regulatory bodies such as the FDA. So the question I'd like to try and answer here today is why, or what type of AI ML can I put into a design given the current market requirements and environment? And I hope to give you some insight on that. So let's see, there we go. So there's a lot going on. There's a lot of big challenges and opportunities going on in the healthcare market overall. I mean, the big picture idea is, how do we treat more patients? How do we reduce the overall costs? And how do we improve the outcomes? And those are the big picture things that are happening. And big driving issues, many of them for healthcare, is things like remote and virtual healthcare, and telehealth is a part of that. We have device security when it comes to devices that are going onto the internet and edge computing and the connectivity issues. Overall security there is a big important factor. The next part would be also large database security, which we unfortunately hear a lot about in the news when we have big data breaches. And finally, what I think is really one of the underlying technologies that's important to healthcare right now will be artificial intelligence and machine learning based care. So we'll keep those things in mind as we move forward throughout this. So what's the market status as we looked at AI/ML in healthcare? Again, you can see what I put on the slide. There's a lot of potential in the marketplace. There's new insights and lots of data generated, training models. It makes medical health providers' jobs easier. It should make patients' lives easier, better quality of life issues and things like that. You can see the market is growing a lot. From one of the market estimates we've got there, it's growing by over 24% compound annual growth rate. And even if you half that and say, okay, I'm not sure it's going to grow that much, even a 12% growth is pretty hefty. But I think we're seeing more on the higher end of it because there's just so much happening in AI/ML, not just in healthcare, but in all the markets we're looking at. So because of all that growth, all that push by the medical device companies to go into artificial intelligence and machine learning healthcare-based devices and design those things, the FDA is developing a total product lifecycle regulatory framework for it. Interesting thing we see, I mean, as medical device manufacturers push forward, one of the aspects we want to look at too is what's going on with the FDA, what's going on with, say, radiologists, for example, that are looking at imaging, because we see artificial intelligence, machine learning getting into imaging quite heavily, where all the images are enhanced by AI/ML. And back in 2020, the FDA sent out or they had a town hall or something along those lines where they would say, they proposed for a fully automated AI/ML device set up for imaging, where they would go ahead and there would be no physician intervention. And they got a letter back from a group of radiologists that said that it was too premature. Let's not do that. So the FDA has been kind of taking a slower approach to it. But in Europe, where they feel like they've got a lack of radiologists, they're pushing forward. In 2022, they approved a device that would look at simple chest x-rays and to enhance those and make it a fully automated system. So again, and that's a few years ago. There's more and more out there. We're seeing it actually coming in. The FDA is slowly but surely certifying devices. And an interesting study came up as far as utilizing what the concern is. There's a lot that can be said for it. There's a lot that can be said against AI/ML as the FDA is trying to look at this and set up that regulatory framework. But there was one study that was kind of interesting, in that they sent out images to a group of radiologists, and they made an assessment whether there needed to be a biopsy on this patient. And 30% of them came back and said, no, I don't think we need to, or we do. But then when they sent it back later, the same images to the same radiologist, 20% of them came back with a different evaluation. So again, the thing we want to look at is there is some human error involved even in the current system. AI/ML by itself may cause a lot of problems until we get the technology more advanced. How do we marry those two together? And it would be basically similar to what you would do on an airline. If you've flown an airline, you may know that most of the flight is done by autopilot. The pilots are there supervising it as human beings, well-trained human beings. They're supervising the autopilot in case something goes wrong or something is amiss, but they can evaluate that. And the idea of the model is right now that AI/ML for imaging, and as we move forward into other areas in medical device design, will have a component where it can be reviewed or handled by humans more and more, now at least, and then more and more it will become more automated over time. So what's going on with the FDA? A lot of things are happening because of that. Again, they're trying to adopt this framework and see what's appropriate. What will really be safe, what will be effective. That is their job. And then again, not holding back too much on the what the medical device companies are needing, the requirements they're getting from their customers, which are the hospital chains and clinics and other medical professionals they're looking at. They want to allow only fairly modest changes for now. They basically don't want to change the overall functioning of the device, such as enhancing medical imaging output or small customization models for personal vital signs monitoring. Or, excuse me, that is what they would like to do at this point, taking it slowly. Those are areas that they can. Again, reviewing imaging, looking at customizing vital signs monitoring. Those are areas that they are looking at now and improving those types of designs, and more will be coming. But as of last October, the last bulletin that I could find from the FDA, they had not approved anything that was generative AI or anything along the lines of a language-based model like ChatGPT. And the last thing, it's an interesting point. The last thing I could find as of last month was that there's slightly less than 900 devices that AI ML generated, or AI ML medical devices that have been submitted to the FDA. And it's not just the US thing, as I've been mentioning with the FDA. We got 3 regulatory bodies, the FDA, Health Canada, and the United Kingdom's regulatory body, that are looking at 10 guiding principles to make sure that it's safe and effective. And some of the things are really interesting with that, because I like the guiding principles they're using it, because they want to say, let's look at other markets and see what can be used and applied from other markets as well, and making sure that they work for healthcare and they're safe. But let's take some of the ideas that are good out there and utilize those, as well as also creating our own within the healthcare market. So let's go ahead and look at some of the devices that would utilize that. Some of the categories we're seeing along the way. It's interesting that predictive maintenance is one. We're seeing that more in the industrial space, but we're seeing it more and more in healthcare also. We've got ventilators, CPAP machines, oxygen concentrators, other respiratory devices that use motors, and other devices that use motors that can use predictive maintenance basically to say, we see an anomaly happening with this motor, which would not necessarily be caught by anybody who's nearby. Maybe there's not a sound that's weird, but it could be caught by the firmware and the artificial intelligence machine language, and know that device that needs some servicing before it goes out completely. It can also reduce the cost of care in that regularly scheduled maintenance may not be have to be scheduled as often. It can be spread out, thus saving some costs. One of the areas that I've seen that's really kind of interesting is patient monitoring. Look at things in the hospital, in the clinic, portable wearable devices, seeing AI ML being adapted into those areas, in things, as I mentioned before, customization of your vital signs. Everyone's ECG waveform, for example, is different. It's a signature that some companies even use to utilize security measures. But since your ECG profile is different, other aspects, respiratory things like that, can be different. Those can be monitored and analyzed by the artificial intelligence machine language algorithm to say, hey, look, for me, for example, when it's monitoring me, I can tell that I'm okay or there's a problem versus somebody else. Because since the waveforms, for example, for ECG vary so much, one patient may look fine, and then another, if you take that device to another person, they may worry that there's some kind of arrhythmia going on or something that's not right. But in my case, for example, it would be fine because it already has learned my waveform. Other areas, of course, are imaging, MRIs, ultrasound, CT scans being used heavily in those areas, and more growing in that area. And some of the other areas we're not hearing so much about, but I think are growing, are areas like drug delivery and drug development, robotics, and prosthetic limbs. Prosthetic limbs are kind of interesting because, again, you're customizing to the person who's utilizing that. And that's where the machine learning can really take off and be a great quality of life help. So what are some of the other devices? Well, I think kind of the sky's the limit. If someone's not already looking at machine language and AI in these types of devices, it's coming. And we've got all kinds of devices I know that we work with as far as our medical clients, home use devices, wearables, portable, in clinic, out of clinic, someday even implantables. We're heavy into implantables. We work with companies that do that, class 3 designs, but we'll see more and more over time in this whole area. Slow but sure, but we're seeing more and more, especially in imaging and I think in patient monitoring right now. So exciting stuff's coming. So what does that model really look like? Well, for us, we see ourselves as giving the basic building blocks for AI/ML. When it comes to healthcare, with the experience and time we've got in that, we offer obviously a lot of different things, but we've got a support model that says we want to offer as much as we can. We make MCUs, MPUs, multi-core FPGAs, all the different types of compute engines. And we build from there on our other things, software, our analog chains, signal chains and processing, connectivity, security, operating system support, other types of support, the tools, including the tools which Neelam will talk about for AI/ML, and ultimately supplying all of that. So the basic model is we build from there, and you take it from there to build your models up, and then obviously writing your code, the learning models, and your certification and approvals from your government regulatory bodies such as FDA or EU MDR. So with that, I will go ahead and turn the time over to Neelam to go more in depth on AI/ML.
Thanks, Martin. Hi, everyone. Thanks for joining us. So I have a few slides that we will walk through. Primarily, we are trying to share some of the challenges that we see in implementing AI/ML into embedded devices, both in medical as well as non-medical industrial field as well, and places in places where we can help and how we can actually help addressing those challenges. So this slide talks about standard flow of implementing any software or any project for most of the embedded projects. But there are certain areas in each of these steps on the flow where AI/ML brings in special challenges or bring in some differences than a standard embedded software or hardware development. So maybe we can start with the project goals on the left. As always, an embedded engineer or a manager would start out with a clear articulation of the goal, what type of customer advantage or benefit you want to offer with a given project, what type of competitive targets you want to achieve, and the cost and performance. The difference here with machine learning implementation is that there are not too many. It's brand new area, practically being implemented for the last 2-3 years and growing so fast that there are not too many examples of what can be done and what is difficult to be achieved. What is the right goal to implement in ML versus traditional heuristic-based algorithm, etc. And this is where we can help. We can work with clients to decide and consult that, hey, for example, if you are looking to improve, let's say what Martin said, predictive maintenance for motor, is this the right thing to implement in what type of devices? If you do implement machine learning, what kind of data and models that you will need to implement such a thing, and how it will show up in your cost and performance targets. So we can provide help in evaluating different trade-offs, different options, and also bring in, we work with many partners, so bring in partners' expertise in enabling you to set the right project goals, and also work through feasibility and planning. When it comes to feasibility and planning, one of the major challenges with implementing machine learning is actually to get data which can be used to train the models, right? So for example, you need to train an AI model with both examples of what is a normal or routine data point, and also a data point that says, this is what I want to identify, this is different than normal, right? So for example, if you want to identify a specific area in an image that you take out of ultrasound equipment, you need to be able to train the model for both regular data point as well as specific image that you want to separate it out. And that becomes very challenging for a lot of players who are not used to operate this way. And so that takes specific expertise and investment than just traditional embedded software development. The third area, which is in the middle, is really implementation. And if you think of implementation, many times we see project engineers start out with proof of concept. Say, okay, I want to implement something on machine learning. How do I do that? So when you try to do proof of concept, one of the tendency we see is just take, what's more well-known or famous platform, either from, NVIDIA, Jetson, or something like that, And then you really implement proof of concept of what you're trying to do, whether it's image processing or predictive analytics. And it's somewhat standard and easier to go ahead and do that. But the result comes out to be maybe 10x the cost of what you can actually target, or maybe even 20 times the power consumption that your target application can support. So what you want to do really is avoid that proof of concept work with a target silicon that you're not going to be able to achieve and take it into production at all, and look for right optimum silicon and software platform, which you will be, be able to use that into your production version. So both of those, feasibility planning and implementation, we can help our clients offering multiple silicon platforms. So, and I'll talk about that in the next slide, where we offer you a range of silicon platforms for a variety of different ML algorithm implementation, as well as offer ready-to-use software and hardware kits for developing those proof of concept for your projects. The next obviously comes, once you implement a algorithm, you need to test it out. You need to first test it in lab environment, and then you also need to do some real-world testing and production testing. And then after that, you're gonna look for quality, reliability, lifecycle upgrades, etc. So once you think through those aspects, you suddenly realize that you need to think about a platform that supports you through the life cycle. So for example, as Martin mentioned, we have supported many clients to implement variety of different solutions into medical grade. And also, we come with a background of providing defense and space grade silicon platforms that provides A, very high reliability, and B, very long life support. You don't want to end up in a silicon which everything works fine and you get everything well, but 3 years down the line, you actually need to change it because that silicon supplier is now no longer supporting that device, and they are moving on to the next fast moving thing. So the benefit of working with Microchip is going to be a long life support as well as very optimized silicon platform alongside the consultancy and software and toolkit that we can provide. So hopefully this makes sense in how we can help. Now let's take a look at different silicon platforms that we can offer. What this slide shows is really implementing machine learning in a 3 different buckets when it comes to silicon platforms. And they're somewhat aligned with sensors, the type of sensors, type of algorithms you want to implement. For example, if you're implementing image processing type of project, it's it's going to be real time. It needs certain amount of compute power and certain amount of sensor interfaces for cameras or infrared cameras or RGB cameras and so on. So we provide that type of platform in our FPGA, field programmable logic devices. And the family is called PolarFire SoC, which also has an embedded microprocessor. And in those platforms, we offer ability to implement real-time, near real-time, high frame rate, large image size processing, multiple input streams, and also simultaneous neural network implementation. In general, that class of silicon will run, half a watt to 3 watts, so 500 milliwatts to 3 watts type of power consumption, which for a programmable logic is almost half of anybody else can provide. The middle bucket you see is what we call smart HMI, human machine interface. What we put in here is typically gesture recognition, but also audio recognition, maybe touch recognition type of algorithms. And for these type of algorithms, you do not need high compute power like you need for image processing. And so this is typically achieved in smaller, less compute power devices like the SAM A7 and A5 platforms that we have, as well as the DSPIC platforms that we have. You're going to implement this in something like 100 milliwatt to 1000 milliwatt power consumption for the chip. And that's very highly suitable device for this type of application, including maybe even a single stream camera application. The third bucket we are showcasing here is what we call smart predictive maintenance, which is really a time series data. You're sensing linear sensors, for example, temperature, voltage, current, pressure. You could even use multiple sensors together, but ultimately each of these sensors doesn't need too much high compute power for implementing machine learning algorithm related to those. And so we're able to actually implement that in a microcontroller, both in a standard ARM 32-bit microcontroller like SAM-D21 from Microchip, as well as we are probably very unique in the industry who is supporting even down to 16-bit or 8-bit microcontroller as a silicon platform for implementing linear sensor algorithms for predictive maintenance. And I'm talking about machine learning algorithms down to 8-bit or 16-bit microcontrollers that provides you a very low cost, but also very, very low power and a very small footprint to be able to implement those algorithms. So hopefully this provides you some picture of different silicon platforms we can offer. Alongside the silicon platforms, obviously we offer development workflow. For the most part in the industry, you find TensorFlow and similar framework is where most AI engineers start developing AI algorithms around that. So we support output of most of those frameworks, specifically on TensorFlow as well as TensorFlow Lite and ONNX or PyTorch or many variety of framework, down to 8-bit microcontroller, because that's somewhat unique in the industry. We actually have our own MPLab ML platform that supports you all the way from data collection, data analysis, and training machines down to the implementation. So that's about the framework. The middle section shows interface, which is something that we provide for anybody to implement output from a framework and put it in the silicon. And of course, each of the silicon have their own specific silicon implementation framework that we can provide as well. So this gives you more complete overview of development flow. Let me take example of a total system solution, and this is example of a smart embedded vision, which is really a camera-based sensor that we can provide. What we are showcasing here is that we not only provide a silicon platform to implement machine learning algorithm, but we also provide many other silicon components around it, as well as when it comes to platform like FPGA, programmable logic, we provide functional blocks inside those programmable logic. So for example, programmable logic can support different type of interfaces for sensors. So we support MIPI, we support SLVS, etc. And each of those sensor interfaces are implemented as part of logic in the device. Similarly, on the other side, we support display interfaces. In the middle section, we provide a set of IP blocks that can be implemented for image processing. So you can literally build up a very specific image processing pipeline. And the advantage of such specific pipeline is that you are implementing it in a smallest footprint possible and consuming lowest power possible in that particular device. And of course, there's a deep learning inference engine that we talk about in terms of vector blocks in the previous slide. And that will also be implemented in programmable logic alongside other interfaces required. And as you look surrounding the PolarFire chip, you'll find that we support power management devices, power supply devices, as well as timing devices like oscillators, clocks, etc., and the PHY and the Wi-Fi controller interfaces. So you can find complete solution from us, not just silicon platform, not just development toolkit. And what we have available today, so we believe in offering starting points in for machine learning. So we have library of demos or starting point functions available. We call microchip inference functions. And here is a long list of some of those functions available. I'll not go through everything, but I'll point out a few things. You can see, for example, we can offer a person detection or a face recognition for, let's say, access control or privacy reason, gesture recognition, people counting. On the other side, audio, voice command, or equipment aging, anomaly detection with fan vibration, gas leakage, etc., etc. And there are a lot more of this continuously being built and put in the library. So for more information on this topic, we encourage you to visit our website, microchip.com/ml. And actually, most of our medical information is also available on these links provided, microchip.com Smart Medical or microchip.com/ml. So thank you for your attention to this. And with this, I'll hand it over to Adam for StarLab presentation.
All right, thank you very much. Thank you everybody for joining us. And my name is Adam Frazier. I'm the CEO at StarLab. I have been doing cybersecurity and embedded security for my entire professional career, which started in the Air Force when I was much younger. And I've moved from there to research to systems architect to business area. So I'm a member of StarLab. We're a very small boutique embedded security company, which primarily we do a lot of work in the defense space, protecting critical applications and data that run on mission critical systems all around the world. And so we bring a wealth of understanding about the security problems that are in the embedded space and as AI moves out towards the edge. It should really be no surprise to anyone on this call that the healthcare industry is very much at risk from cyber attacks and different kinds of attacks that take place. I think most recently in the news, there's been a lot of ransomware activity that's taken place against hospitals and different areas like that. What I found interesting was the healthcare industry actually has the highest ransomware or cost associated with compromise. That really should not be a super surprise. Their attack surface, in general, the attack surface of the healthcare industry is quite large when you think about the IT industry or IT space that exists within hospitals and other medical facilities. And then you add to it the unique devices and everything from special beds to operating room equipment that is constantly in motion potentially, as well as now what's moving into devices that are worn on human beings. So the attack surface, of course, is ever increasing in this space. So in terms of some of the security challenges that exist that are AI related and in the medical or healthcare industry, I wanted to focus on these three potential areas. If you've been around security, a lot of these terms will be consistent or understandable by you because they're quite prevalent. They've been around in security for a long time. The first one I want to talk about is data confidentiality. Obviously, in the healthcare industry, you're talking about potentially lots of patient data that obviously has to be treated in a very secure manner. And in particular, on the embedded space, you might be collecting that data on a particular edge device of some sort, but then offloading that data, transmitting it to another domain like the cloud to do additional processing. In fact, we just saw Apple's release of their Apple AI or Apple Intelligence, and they're doing this, right? They're having a lot of models on devices, but then they're going to have their privacy cloud that is going to use this. So to do that, you need to both protect the data at the edge, but then also when it's being transmitted, and then again when it reaches some data center in the future. And so there are some various solutions that we can bring that can be brought to the table to provide that data confidentiality. In addition to that, there's your output of your integrity. So these models, one of the challenges with many of these models is, of course, they're not super explainable, which means it's often difficult to determine whether they're working properly. Obviously, there's lots of research going on in the adversarial AI space, but I want to bring your attention to a couple other spaces. First off, just because I've been around the community long enough, these models will eventually be reverse engineered. Like I've already started to see research papers into how these models can be reverse engineered so that different parameters can potentially be identified. Different techniques that were used to build the model can potentially be identified. So the protection of the models themselves, particularly at the edge when they might be even most vulnerable, is going to start to grow in its importance. Additionally, depending on the kind of model you've made, a lot of these large language models, you're not exactly sure if any guardrails you might be put in place can be bypassed. And of course, some of that, as we've seen in the news, can create reputational risk for the organization that's using it. So the integrity of the output of the models are going to be very important, which means you need to have some protections built in for this purpose. So we'll talk briefly about some of those. And then finally, sustainability, or what is commonly referred to as availability in the cybersecurity space. As the other presentations have essentially sort of alluded to, greater and greater reliance are going to be put on these AI systems. And if that's the case, then humans are going to be removed from the loop a little bit. And that means the availability of these systems are critical. Now, what that translates into is you can't have a device just potentially be compromised and you just stop it from running. You might actually need to run it even in a compromised state. And that's what we refer to as cyber resiliency. And so one of the things we're going to talk about in a second is some of the protections that you can provide that can give you some of these cyber resiliency capabilities. Here at Star Lab, we have a particular mindset that we apply and really guide our customers through. We call them the 7 tenets. The most important about these tenets is the idea that we assume the attacker is already present. Much of cybersecurity these days is focused on observation or detecting the adversary as they try to get in, which means once they do get in, you have a very weak security set when you get in, and the adversary can cause a lot of impact. Or security through obfuscation, which means you're trying to hide things, which often does not work very well either. We believe in assuming the bad guys in and designing the system from the beginning to be secure. So I'm going to talk about the first 4 of these, not all 7. So threat modeling. This is very, very important, particularly for edge devices that are going to be running AI for healthcare. It is the fundamental first thing that has to be done when you're thinking about designing security into your system. And there's various reasons why, and you can see them here. But let me stress, most importantly, is that it allows you to look at and prioritize what kind of threats you're going to try to defeat or mitigate. Most importantly, this is particularly important when you're talking about devices that are in the physical world. Security is much easier, of course, if you can keep it behind locked doors and maintain access control that way. But we're talking about in the healthcare industry devices that exist essentially in the wild, and those things can be stolen and taken and reverse engineered. They can be purchased by individuals, pretending to be some other entity, again, reverse engineered and exploited. So you need to very much think about the tamper threat when it comes to the physical access of much of these devices. Additionally, I mentioned this before about the data protections, very, very critical for AI in healthcare. This starts with really thinking about how you create what we call a trusted compute base. And what this means is you want to start very much at the lowest level and ask yourself, how do I do secure boot? That's one of the fundamental security principles that it needs to exist, is how do I implement a secure boot solution so that my device will not execute if it is not if its integrity has not been validated. You can slowly but surely move up the software stack and do more and more data protection capabilities, both at rest and at runtime. But these you must think about how you're going to protect the data, both the confidentiality of the data as well as the integrity of the data. Next, we're going to look at attack surface reduction. Attack surface reduction, again, is this idea of limiting the space in which an adversary can attempt to gain access or to maneuver once they have gained access. We really here at StarLab break this down into 3 areas. Very much the most appropriate time to reduce your attack surface is during development. This starts with a very, very sound software development lifecycle that should be looked at from a security standpoint and even an insider standpoint. How do you know that you don't have malicious entities influencing your code base during development? Obviously, very well good testing regimen that includes scanning and fuzzing, and understanding your supply chain. A lot of open source software is being used in the industry, and you should have a good grip on what that is. Additionally, at build time, you want to try to remove functionality. You want to very much remove all those interfaces that you've used to essentially test and verify the functionality of the product. You want to remove those when they go out in the field, in the deployed environment. And if you can, you want to try to make things as immutable as possible. I know this might not be really possible given that you have updates you want to do and whatnot, but you want to think through that very clearly, because the more immutable you can make it, the less action the bad guy can take on the device once they've gained access. And then finally, at runtime, do the proper configurations and patch management that needs to take place to keep a system in a good, secure state. I mentioned this, the immutable configuration, if you can. We very much believe that you want to try to stay away from user-based access controls. Those tend to be the first thing that gets exploited by adversaries, right? They gain root level access, and then once they do that, if you have no other kinds of controls, they essentially own the system. A better way to do it is what we call mandatory access controls. This essentially is the idea of having of assigning access based on resources and the level of or what needs to access resources. So you might have a process that needs to access a particular data file, and you want to assign access only in that way, and that process shouldn't be able to access anything else, and that data should not be accessible by anything else. These are the kinds of things that happen during a mandatory access control analysis. You want to be very you want to ask yourself or very much test before you deploy this idea of immutability, right? So you could potentially create your system too immutable, in which case you need to you'll have some challenges updating. So testing in this space is very, very important to make sure you get it just right before it's released. So in general, what I want to leave you with from a security standpoint is that many of the solutions, or many of the most common approaches to security, are really just not that good. You end up paying a lot of money for them, and what you get is sort of someone to watch your insecurity. You haven't really addressed your security if all you're doing is applying some kind of observability solution or some bolt-on obfuscation approach. In order to survive attacks, you need to think about the adversary being present, and then protect your data and build your system securely from the beginning. At StarLab, we do have a solution that helps with this. We call it the Kevlar Embedded Security Solution. This is a Yocto-based security solution. Over here on the right, you can see in light blue, this is where Kevlar essentially sort of integrates with your different elements of your software stack. This suite of capabilities is highly flexible. You're able to pick and choose many of the security protections that you want to apply based on your threat model, for example. It provides both the cyber resiliency capabilities, so it really diminishes the ability for an adversary once they gain access to create any kind of havoc once they've gained access, and then provides that data protection that we talked about as you capture data and potentially send it off to the cloud. Not most importantly, but very importantly is Kevlar is aimed to fit very much into your existing development process. It comes as Yocto layers. It can be very easily applied to your pipelines. It actually also comes with a test suite so that you can validate that the security that you're building into the solution is actually working and present. Most importantly about this DevOps integration is it really takes out you having to ensure that you've done this correctly. We know in the Linux space it can be hard to do this correctly. You're forced to read a bunch of manuals. But at the end of the day, we've made this very simple, and you don't have to do that. You can know it's being built correctly into your system from the beginning. If you'd like to learn more about these solutions and any ways that we might be able to help you, you can check out our blogs. We have very technical blogs if you'd like to look into those, as well as some just more information on the products and company. All right, well, Rich, I'll turn it back over to you.
Thank you very much, and thank you to all the speakers. So we got a bunch of questions here. I'm going to ask them in no particular order. Out in the audience, we have about 10 or so minutes, so ask your questions. Now's the time. Our experts are here. Okay, let's start with Martin. I saw an item in your slides about Class 3 designs. Does Microchip really, non-believer, does Microchip really supply product for the design of FDA Class 3 devices?
Well, there's some evidence out there that non-believing can happen, but yeah, we do. We've got a lot of experience over the years. As many of you know, involved with healthcare, that the suitability is really determined by the medical device maker. The FDA's term is suitability, and so we've been doing this for a long time as far as supporting Class 3 designs. Most medical designs, even Class 3, utilize standard electronic devices. Ours are our competitors, and we've been doing this for a long time as far as working with clients to get them set up, how to approach that, given the quality and reliability data. And so it's been actually interesting to work that and help our clients do that.
Is it that rare to supply those devices? I'm wondering about the person's non-believerness. If that's probably not a word, but you know what I mean.
Yeah, we've seen that out there. I mean, there are times that it gets to be very difficult, depending on the requirements or the terms and conditions that some companies will sell into the medical space, into healthcare and medical devices. So we're basically set up from many years ago to our terms and conditions of sale and how we support and do all of that. And so working with us, we found that people can do that. And it's been a good process and an easy process, very much less expensive than with other types of solutions, possibly because of not special testing necessary and some things like that in many cases.
Okay. Yet another non-believer. I'm going to direct this one at Neelam. Many systems would need more than one interface / modality to support, such as facial recognition or voice recognition. Does Microchip devices support these requirements?
Yeah, hi, thanks, Rich. Yeah, so that's a really good question. In fact, with ChatGPT and other large language models delivering some of the really interesting outcomes for consumer domain, there is a more and more interest developing in embedded devices also being able to support multiple modalities. And the answer to that is absolutely yes. We actually, like I showed in one of the slides, we have wide range of silicon platforms, and specifically the higher compute capacity platforms like an FPGA or even microprocessor can support more than one interface, more than one modality. So for example, you could have a video and the voice processing being processed simultaneously, and you could create a program that says, if I see this in the picture and I hear this, then trigger this outcome. And yes, that's absolutely feasible with our devices today. In fact, I go step one more beyond that and say specifically in our programmable logic devices, you could go all the way up to 4 different models concurrently operating and delivering on either same modality or different modalities at the same time. So yes, that's really happening, and it's actually being requested increasingly more from our clients.
Okay. All righty. Adam, before I read the question, let me warn you, we only have about 5 minutes left here, okay? Because
No problem.
this could be a whole webcast by itself. Are there any best practices or design principles for building medical devices with a minimal attack surface? Yes.
Yeah.
Okay.
So I would first and foremost, I would very much think of what we call least privilege. This is the idea that you want to really understand the roles of the entities that are on the system, and I don't just mean people. I mean processes that are actually that are running on the device, and understanding that they should only have the privileges they need to do the jobs they need to do. In addition to that, I mentioned this when you build, be careful about what you're building into your system. Ask yourself, are you using for example, a distro or whatnot that's coming with a bunch of drivers you don't need? You have a bunch of interfaces that you're having on your device that you don't actually use, and you have drivers for it. And these are all things you want to be mindful of and potentially remove if you can do so.
Okay. Let's see. Back to you, Martin. Low power wearables were mentioned as an area that we would see AI/ML implemented. How do you get started on designing low power wearables?
That's a good question. Thanks, Rich. There's a lot of aspects to that. What we're trying to do overall, given our background in medical, and we offer a lot of support again. We've also got baseline reference designs that we've developed that basically give you all the basic, for vital signs, for example, when you're looking at wearables and doing medical vital signs with your wearable device, we've got baseline designs that will give you both transmissive and reflective pulse oximetry, so you can utilize, basic heart rate, blood oxygen level, like also for blood pressure, for ECG, different types of things. So again, there's different aspects. You can use these as building blocks, as well as some of our reference designs for wearable devices for movement and environment. So you can build a device basically from the different types of technology, mix and match what you want. As far as, this is a patient's environment. Here's what's going on with their, their body temperature, the environment, their the barometric pressure, whether they're running uphill or something, in their movement, sleep studies, and you can combine that with heart rate monitoring and SpO2 and things like that. So again, giving all of these basic building blocks you can utilize, we offer as building blocks to help our clients build wearable devices.
Okay, excellent. Let's see, Neelam. A common theme in the industry is lack of in-house machine learning expertise. Ain't that the truth? How would Microchip help a system developer to address this?
Yeah, that's a good question, Rich. So this is more common than one would realize. I think in our experience, there are probably only 5% of the companies out there that have, required skill set to implement ML flows completely in-house. And a common perception is also that ML algorithm, you can simply source some models from open source and some data set from open source and just try and train those things very quickly and create something. And that's also true, but the reality is that that when you want to create something that's production worthy, that bears your logo in a product that goes out with specific accurate outcomes, that requires more work, both in terms of selecting data sets, selecting models, but also testing them out and so on. So there are 2 or 3 different ways Microchip can help. One is obviously consulting, providing insight into and having brainstorming sessions, saying, okay, what is feasible, what can be done, what to look for, et cetera, and then planning around it. The second, we work with multiple expert companies in different areas, including medical device implementation. And these companies have what we call partner network. We have partners who have done similar things, high quality implementation of machine learning in a production environment. And we bring them to the table alongside us to help the client to achieve the goals that they're looking for. So I hope that makes it more clear.
Does for me, for sure.
Thank you.
Okay, we got time for one more. Adam, for you, are there any specific industry standards or guidelines you recommend for securing AI-enabled medical devices?
Yeah, I'm glad you've asked this question because I meant to point this out before. If you haven't heard of the Cyber Security and Infrastructure Agency, CISA, I would highly recommend you review their website and the materials they have. They have a very, very good developer's guide for a strong, secure software development lifecycle. It's very thorough. It has lots of good recommendations on best practices. And we at Starlab have implemented essentially almost all of them from that guide. And it very much will help with the development of your software being secure from the beginning. So thanks.
Thank you. Okay, I'm afraid we are out of time. If you asked a question and did not get an answer, one of these guys will get back to you shortly after with an answer. A reminder that all Open Systems Media webcasts are copyrighted, may not be recorded without prior permission. I'd like to thank our three speakers for the great presentations and for answering these sort of difficult questions. Also to Star Labs and Microchip for sponsoring this event. And of course, we can never do anything of these types of things without you, the engineer. So thank you all for attending, and be sure to register for the upcoming webinars in our AI series. Thanks much, everybody.